Hello students, welcome to the class. Hope you people are well. So today our topic is area under a curve. Previously you have studied about functions and how their graphs look like. But have you ever wondered about how can we find the area bounded by the curves in their graphs? Let us see this with few examples. If fx equals to 1 where 0 less than equals to x less than equals to 2, its graph looks somewhat like this, where this line is y equals to 1, this line be x equals to 2, this is x equals to 0. Now as you can see, the area bounded by this line y equals to 1 is a rectangular region, and we can find its formula by multiplying its length with its breadth. So area would be equal to length, which is 2 units, into breadth, which is 1 units, that is equals to 2 square units, right? Similarly, if the area would have been a triangle, a square, or even a circle, we could have found it out using geometric formulas. But what if it's the other case? Suppose this is my function fx, which is defined between the points x equals to a and x equals to b. Now as you can see, this area is not a standard geometric figure. Then how can we find these kind of areas? So mathematicians found a very smart way to approximate this area by using thin rectangles and then adding all their respective areas. How do we do that? Let's see. First, let's break this interval into two subintervals of equal length. Let this be x0 is equals to a, this be x1 point, and this be x2 is equals to b. Now, how do we draw the rectangles? Now, the width of the rectangle is equal to the length of the subinterval, and the height of the rectangle would be equal to the functional value at the right end point of the subinterval. So in the first subinterval, the height of the rectangle would be f of x1. So the rectangle would look somewhat like this. And in the second interval, the height of the rectangle would be the functional value at b. So it would be f of b, which is here. So the rectangle would look like this. Now as you can see, the rectangles completely cover the required area, but they have some extra area in them too. That means our approximation is rough, it's not accurate. So now let's break this interval into three subintervals of equal length. Let this be x1 is x1, let this point be x2, and then naturally it becomes x3 is equals to b. Then as we done previously in the first rectangle, the height of the rectangle would be f of x1. For the second rectangle, the height would be f of x2, and in the third rectangle, the height would be f of x3, that is f of b. Now, as you can see, our approximation is still rough but finer than the previous one. So, we can observe a thing that whenever the number of subintervals increases, the length of the subintervals decreases and our approximation becomes finer. So, if the number of subintervals tend to infinity, then my points would be of the form x0, x1, x2, up to xn, where n tends to infinity. And in that case, the length of the subinterval will be infinitely small. So let dx is equals to infinitely small length of subintervals. In that case, area of the curve would be the sum of all the areas of the all rectangles. So that would be limit n tending to infinity summation I equals to 1 to n. Now observe, area of any rectangle would be its height into its width, and height of the rectangle is the functional value at its right end point of the subinterval. So that would be fxi into its width. So width we have taken dx. Now this is equal to integration a to b fx dx. Now let's verify this with the help of an example. But first let's write it somewhere so that we can use it later. Limit n tending to infinity summation I equals to 1 to n fxi dx is equals to integration a to b fx dx. Sorry, here it would be equal to. Okay. Let the function be fx equals to x square, where 0 less than equals to x less than equals to 1. So my function looks like this. Let this be the point x equals to 1. This is x equals to 0. Now number of subintervals and the corresponding area. Let us take the number of subintervals to be 3. Then my points would be x1 is equals to 1 by 3, x0 is equals to 2 by 3. Now let's construct the rectangles in the similar fashion. We have, this is the first rectangle, this is the second rectangle, and this is the third rectangle. Okay. So the area would be the area of first rectangle, that is width of first rectangle, which is 1 by 3, into height of the first rectangle, that is f of 1 by 3, plus area of the second rectangle, which is width of the second rectangle, that is 1 by 3, into height of the second rectangle, that is f of 2 by 3, plus area of the third rectangle, where width of the third rectangle is 1 by 3, into height of the third rectangle would be f of 1. Taking 1 by 3 common, I have fx equals to x square. So f of 1 by 3 would be 1 by 3 square, that is 1 by 9. Similarly, f of 2 by 3, it would be 4 by 9, plus f of 1, that is 1 square, is equals to 1. Now that is equals to 1 by 3 into 1 plus 4 plus 9 divided by 9, which is equals to 14 by 27. Now this is equivalent to 0.518518. Okay. Now if the number of subintervals is 9, we can easily see that it would be 0.390496. For 99 subintervals, it would be 0.33840, and for 999 subintervals, the area would be 0.333338. Now as you can see, as the number of subintervals tend to infinity, the area tends to the value 0.3333 and so on. Now let's verify this value by doing the integration within the given limits. So integration, the given limits are 0 to 1 and fx equals to x square. So x square dx is equals to, the integration of x square is x cube by 3. So x cube by 3, where the limit grows from 0 to 1. Now this would be equal to 1 by 3 minus 0 by 3. That is equals to 1 by 3, which is equals to 0.33333 and so on. Now from this we have concluded the fact that we can find the area under any curve by simply integrating that function of the curve within the said limits. So this was about today's class, and in the next class we will be studying the area between two curves. Thank you.